LeetCode 314, Binary Tree Vertical Order. Traversal isn't just another tree walk. It reflects real-world systems, like UI layout engines, spatial indexes, and telemetry views, where position matters. Our mission? Traverse nodes top to bottom, column by column, left to right within ties. This one tests more than traversal. It tests your ability to impose structure and avoid waste. Let's kick things off the classic way. Brute force with depth-first search. We'll map nodes by their grid coordinates and sort later. Time to wade in. First up, handle the edge case. If the tree is empty, we skip everything and return an empty list right away. To group nodes by vertical columns, we'll set up a hash map. Each key is a column index, and the value is a list of nodes, each tagged with its row and value so we can sort top-down later. With that in place, we launch a recursive DFS from the root, starting at row 0, column 0. As we traverse, we'll populate our column map with each node's position and value. Once all nodes are logged, it's time to organize them. We extract the column indices and sort them so we can build our final answer left to right. Now we prep the result list. For each sorted column, we'll grab and process the node entries it holds. In each column group, we sort the entries by their row value to respect top to bottom order, since nodes at the same column may be stacked. Once sorted, we extract just the node values from each entry and tack them onto our result as a column list. After finishing all columns, our vertical order traversal is ready. We return the assembled list. Now let's zoom in on the DFS helper. If we hit a null node, we stop. That's our base case to cut off recursion. Otherwise, we record this node's row and value in the table under its column. That's how we build the map we'll later sort and organize. Then we recurse down to the left child, shifting column index by -1, and do the same to the right, shifting by +1. Row always increases by 1 as we go deeper. This version runs in big O of n log n, mostly due to sorting each column. With n nodes, space is also big O of n. Watch out for deep recursion if your tree is unbalanced. But we can do better. The real bottleneck here is sorting, so let's drop it entirely by using breadth-first search to keep things ordered as we go. Again, we start with the quick sanity check. If the tree's empty, we're done. Return an empty list. To organize values by column, we use a hash map again. But now, we'll add a queue for our BFS, pairing each node with its current column index, starting from 0 at the root. To know our column range, we'll track the smallest and largest column indices we encounter as we traverse. Time to run the BFS. While nodes are in the queue, we process one at a time, always pulling the next node and its column index. We drop the node's value into its column list, creating that list on the fly if needed. We also update our min and max bounds for the columns. Then we toss the left and right children into the queue, adjusting their column indices by -1 and +1 respectively. Once BFS wraps and all nodes are grouped, we build the result list by walking from the leftmost to the rightmost column index, collecting values in order. With all column values assembled, we return the finished vertical order traversal. This version runs in big O of n, no sorting, just clean traversal and grouping. Space is still big O of n, but it scales better and handles large trees with ease. A solid pick for production and interviews alike. We began with a DFS that grouped nodes by column but needed sorting, decent but inefficient. Then we leveled up with BFS, tracking positions live and cutting out sorting altogether. That took us from n log n to n, a big win for scale and speed. This isn't just about trees. It's a strategy for any system where order, position, or structure matters. Keep hunting for those patterns, keep sharpening your tools, and remember, the best coders think clearly, debug fast, and always keep their cool. See you next time.